We are here at the network layer with an overall goal of interconnecting heterogeneous networks in a scalable fashion. A very important device that operates at the network layer is the router. Let's see how it looks from the inside. Here is a router that is interconnecting three networks. Two are Ethernet and one is token ring. Here I have represented the router with 3 input ports and 3 output ports. Each input-output port, for example here, is hooked to a link which is driven by what is called a line card. So here is the block diagram of the router. It is basically made up of 4 parts: input port, switching fabric, output port and routing processor. So an input port basically terminates the physical link. It performs the necessary link layer functionalities. In the more recent routers, the table lookup, that is looking up at the forwarding table to decide which output port the incoming packet has to be forwarded to, is also performed at the input port. It can also queue packets in case the switching fabric is busy, and not only that, the routing protocol information that is received is passed from the input ports to the routing processor for further processing. Whatever packets that are coming from the input port to an output port are often queued and then transmitted on the outgoing link. To transmit before on the outgoing link, the necessary data link as well as physical layer functionalities are performed on these packets. Now, switching fabric basically connects the input ports to the output ports. We will see more of this shortly. And the routing process basically executes the routing protocols and it maintains the forwarding tables. Note that if the input port is also doing forwarding, a shadow copy of the forwarding table is maintained here. Now it is the responsibility of the routing process to ensure that these shadow copies are consistent with the forwarding tables that it maintains. So whatever functionality a router performs can be divided into 2 types. One is called data path functions. So these are the operations that are performed on every datagram. This includes things like deciding where to forward this datagram, calculate the checksum. This is the internet checksum that we talked about before, and also how to schedule this particular datagram on the outgoing link, first in, first out, or some other scheduling. The data path functions are often implemented in specialized hardware for high-speed purposes. Basically, as soon as you get a packet, you want to send it out as soon as possible. For this, you need to process it really fast. The control functions are those operations that are performed infrequently. Basically, for example, packet exchange for routing protocols or system or network management. These are often implemented in software. So in 1980s, which is the first generation of routers, they followed this type of architecture. You had these line cards that drive a particular link. There are many of these line cards because router typically has multiple interfaces. These line cards are connected to the routing process via a shared bus backplane. So this is the switching fabric that we were talking about earlier. Now every packet that is received goes through this bus to the memory for further processing. So as you can see in this case, the processor is involved in the processing of every packet and thereby becomes the bottleneck. If you convert your desktop as a router, for example, this is how the packets will be routed. But this is too slow for regular routing. So in this particular case, how many times does the packet go through the bus? Right, twice, once from the line card to the memory and then back again from the memory to the outgoing port. The second generation routers try to address the shortcoming of the first generation routers where the processor is becoming a bottleneck by involving more parallelism. The parallelism here is in the form of moving the CPU memory functionality into each of the line cards. So now all the forwarding functionality is handled at the input port itself, as I mentioned earlier. So in this case, how many times does a packet travel the bus? just once, because once you decide what your outgoing port is, you definitely don't have to go through this CPU because the CPU is already decided which outgoing port. So you just go through the bus to the right outgoing port and then exit the particular router. So what's the problem here? Basically, the bus becomes the bottleneck. So for example, if you're using the bus to transfer a packet from this line card to this line card, if this line card has a packet to some other line card, it just has to wait till the bus becomes free. If these line cards, for example, are operating, let's say at 100 Mbps, and let's say you have 16 of these line cards, how much do you think this bus speed should be so that there is no queuing going to happen as part of the line cards at the input ports? So the worst case happens when each of the line cards are receiving data at 100 Mbps. So if you don't want any queues to build up as part of your line cards, your bus should operate at 16 into 100 Mbps, that is 1.6 Gbps. What if these line cards are 1 Gbps links? Then your bus has to operate at 16 Gbps. Now there is a limit to how much speed this bus can operate. As you increase the speed of your line card as well as the number of ports, there is only so much speed the shared bus can operate at, in which case this becomes a bottleneck. Then how can you overcome this particular bottleneck? So the third generation routers went for what is called a switched backplane. Basically, you have a series of buses. So if you have n input ports and n output ports, you have a total of 2n buses with n into n cross points. These are the cross points. Basically, you handle it through additional parallelism. In second generation, the parallelism was in the hardware, where you replicated the CPU memory functionality in each of the line cards. In the third generation, apart from this, you are replicating the buses. So in this case, as shown, multiple transfers are possible. For example, if you have a packet coming from input port 1 to output port 3, this goes in this particular fashion. At the same time, a packet that is coming from input port 2 to output port 1 can take this path. By the way, this input ports, output port for a given line card, so for example here input port 1, output port 1 correspond to the same line card and are implemented as part of this memory. All recent routers employ this particular architecture. Whenever a packet arrives at the router, you want the packet to experience the least amount of delay, as well as preferably not experience any losses. Both these, that is minimizing delay as well as losses, can be achieved by high forwarding speeds. That is, as soon as you get a packet, try to get rid of the packet out of the router at the earliest time possible. Why is this true? I'll get to that shortly. One of the components of these high forwarding speeds is the lookup speed, basically the time it takes to determine which outgoing port the incoming packet has to take. Now this forwarding table lookup, as I mentioned, happens at the incoming port itself. Ideally, you want this lookup speed to exceed the line speed. What do I mean by this? So for example, you have a line speed of, let's say, 1 Gbps and you're getting packets on this. For each packet, you have to look at the forwarding table and decide which port it has to go to. Now suppose, let's take the worst case, where you have packets that are 40 bytes are coming as part of this 1 Gbps link. Ideally, you want to finish the lookup of this packet before the next packet comes. If you don't finish the lookup of this packet before the next packet comes, then you are going to build up the queue and this is going to result in packet losses. So for this particular case where you have an input line speed of 1 Gbps and 40 byte packets, how much should your lookup speed be? So basically, when you get 40 byte packets continuously on a 1 Gbps link, you're basically getting 3 million packets per second, and this implies that your lookup speed itself has to be greater than 3 million lookups per second, because for each packet you're doing one lookup. This implies that each lookup should happen under 8 nanoseconds. By the way, this 40 bytes is rather a worst case scenario. Typically you get packets that are bigger than this, but this size really stress tests the system. So there is a lot of research that goes on in how to improve these lookup speeds. Another important component of the forwarding speed is the switching fabric speed, basically the rate at which packets get moved from the input to the output. Now when you have n input and n output ports with identical line speeds, there will be no queue buildup at the input port if your switching speed exceeds n times line speed. This also results in no loss. Why? What is the worst case that can happen? Worst case will happen when all the input ports are operating at line speed. So you have n such input ports, all of them are operating at line speed. So the aggregated input rate is n times the line speed. Now if you have a switch that operates at greater than this speeds, the queue will not build up at the input port because you are transferring the packets quickly to the output ports. However, queues can build up at the output port because the output line is operating at the line speed, and in the worst case, if all these input ports have packets for the same output ports, then your incoming rate is n times line speed, whereas your outgoing rate is only line speed, in which case the queue will start to build up and you have to drop packets because there is only so much space, memory space, that you can allocate per output port. So increasing the switching speed by clever architectures is another area of research in the router design. So in summary, a router is a very important device that operates at the network layer. It has many components: input-output ports, switching fabric, and a routing processor. So over the years, it has evolved with better and better forwarding speeds. Its performance is dictated predominantly by the stable lookup as well as the switching speeds. Now that we know how a router operates, up ahead, let's look at the IP protocol itself, where we will see the packet format as well as the fragmentation and reassembly that is necessary to do as part of the IP protocol.